So let's start. So this is, let me tell you what the course is about. It's Quantum Field Theory 3. So I'll be teaching the first week. So my name, if you don't know, is Jaume Gomis. And my office is 427. So in the first week, I'll be introducing to the topic of the subject of conformal field theories and the various applications that it has and the recent progress that has been achieved in this subject, even though it's a very old subject. The second week, and this will be in a general discussion, not pertaining to a particular dimension. Then in the second week, Gan will talk about the amazing properties of two-dimensional conformal field theories. And the third week, Daniel, actually I'm not 100% sure, but we will talk about instantons, monopoles, whatever. Kind of semi-classical aspect of quantum field theory. Very good. So in this first lecture, what I want to do, essentially try to motivate the question of why this funny sounding, okay, so why conformal field theories? Why should we care? Why are they interesting? Where do they appear in physics? What have they taught us? So today will be more of a qualitative discussion of where this subject enters in physics. Also it enters in math, but I will not have anything to say about that today, but it also has many applications in math. And then tomorrow we will systematically be building the theory behind conformal field theories and explicitly see some of their main features. Okay? Very good. So please feel free to ask me anytime, otherwise I get bored here. Very good. So, the key word here for now will be is the word, well, conformal is one word, and the other one is field theory. So what is the property of a conformal field theory? So a conformal field theory is a particular quantum field theory that has extra space-time symmetry. So here I use the word space-time to distinguish it from, say, standard global symmetry. So you can have a theory that has global symmetries, and of course, quantum field theories have typically many, at least classically, many global symmetries. Here we're talking about a very specific and a very special type of symmetry, which is a space-time symmetry. So these are transformations that act on space-time. So what are the kind of space-time symmetries that we are familiar with from before? So for example, so in the relativistic context, we're used to Poincaré symmetry. So that's importantly the space-time symmetry associated to relativistic systems. Okay. And in the non-relativistic context, you can have theories that have Galilean symmetry. So these are two examples of space-time symmetries that, in a sense, any quantum field theory has. Essentially, by definition, a relativistic quantum field theory is a theory that's invariant under a particular connected subgroup of the Poincaré group. Okay? And a Galilean symmetry is one that is invariant under the Galileo group. There are theories that need not have these space-time symmetries. They could have a smaller set of symmetries, but this will do for our discussion.
Is Galilean symmetry only the translation?
Sorry?
Galilean symmetry only the translation?
No. Okay. No. So okay. So good. So it has everything. So well. So by Galilean, strictly speaking, you mean that you have time translations, you have spatial translations. So I'm writing the generators of the transformation. You can have rotation, spatial rotations, and then you can have, so the funny one is the Galilean boost. And actually, typically, Galilean theories can have also an extra U1 symmetry. Let's call it Z. That's usually associated to particle number conservation. And that, for example, appears in the classical theory as a Poisson bracket, in the quantum theory as the commutator of the spatial translation generators and boosts. Give you this extra. This is an central extension, so it's a chart that commutes with all the other generators, but appears in the right-hand side of the commutator of PM of translations and boosts. It is important to say that there are many interesting systems in condensed matter physics that need not have this symmetry. So, for example, yeah, maybe I'll give you an example. And just a comment that maybe is interesting is that it is precisely because Galilean invariant theories have this extra U1 symmetry that the Galilean theories do not have particle production, unlike relativistic quantum field theory. Okay, so these are in a sense, the space-time symmetries that any quantum field theory, relativistic or non-relativistic, has. A conformal symmetry is an enhancement of the space-time symmetry to a conformal symmetry. Okay. Now, in the case of relativistic invariant field theories, there is a unique notion of conformal symmetry that we will study very carefully. But it turns out that in Galilean systems, there are several inequivalent notions of conformal symmetry, depending what the generators of the conformal symmetry are. So you can have something that, for example, so here you can have several notions. In a non-relativistic case, you can have several notions of conformal symmetry. Like you can have something called Schrödinger symmetry. So this will be the maximal symmetry. It has this name because it is the maximal symmetry of the free Schrödinger equation. Or you can have something called the Galilean conformal algebra. So when we talk in the non-relativistic context and we talk about conformal field theory, we have to give more information on whether we're talking about one or the other. Yes?
When you say a certain theory has a certain symmetry, what exactly does that mean? That your action is invariant, or? This
is what will mean, so that the reaction is invariant. But okay, one very important thing about conformal field theories is that conformal field theories, one thing that's remarkable about them is that you can axiomatize how you talk about them, and you can essentially do not need to talk about the action. You can get away by talking about operators and states. So in that context, what it will mean to have a symmetry will mean that there is a conserved current associated to that symmetry. When you have a Lagrangian...
So anomalies don't count?
Sorry?
Anomalies don't count.
Anomalies don't count.
Like it needs to be a quantum symmetry, not something that can be broken by quantum.
Well, as we will see, anomalies in conformal symmetry will play an absolutely crucial role. But the problem is that, yeah, so let's postpone that. So I will allow to have a conformal anomaly, but of a very particular type.
So that still counts as a symmetry?
Yes, okay. In flat space. In the absence, so without drawing a big discussion, the issue becomes whether a symmetry, so you can have violations, anomalies in your theory in flat space, and then these only appear as contact terms in certain correlation functions. And they only become true violations if you couple your theory to some background field. Like instead of putting the theory in flat space, you put it in a non-trivial background metric. But the correlation functions of an anomalous theory in flat space will satisfy the conformal word identity. So in that sense, it's a symmetry. Even though there is a contact term, there's a violation at coincident point. In one lecture I hope to get, I will discuss this in detail. Okay. So, and the thing that's remarkable about conformal symmetry is that, in a sense, this is the largest space-time symmetry group that any quantum field theory that is non-trivial can have, at least above 2 dimensions. In 2 dimensions, there are peculiarities. You can have theories that have a bigger space-time symmetry, but above 2 space-time dimensions, this is the biggest symmetry that a non-trivial quantum field theory can have. This also can be, there's a slight loophole. If your theory has fermionic generators, then the biggest symmetry is what's called superconformal symmetry. But here we will be only discussing theories that have bosonic symmetry. Okay. It got stuck. Okay. Okay, so let's start with what are these conformal symmetries. So this, of course, we'll study in a lot of detail what the geometry, what are the space-time transformations. But let's start with one transformation that is obvious. Let's start with the scale transformation. So, of course, this play a fundamental role in physics. In a sense, even though we may not be thinking about it explicitly, but you know, it has been implicitly in the work of all science since the very beginning. In the question of when we study a given physical system, you have to decide at which length scale you're probing it. Well, and depending on which length scale you probe it, you have a different description of the system. So, for example, if you study water in that glass macroscopically, you can get away with hydrodynamics. But if you go to very short distance scales, you will have to study it using like the Schrodinger equations of atoms and so on. So we are always thinking, when we think about the physical system, we're always implicitly thinking at what scale are we probing it. Okay? So we are accustomed to asking what happens to a physical system as I scale, which means zooming in or zooming out of the system. How does the physics and the description of the physics change? Okay? More mathematically, what is the scale transformation? So for rotational invariant systems, especially rotational invariant systems, what we ask is what happens if I take my spatial coordinates and rescale them by some parameter lambda. So this is like zooming in and zooming out in Google. And in general, I allow different scaling of time than space. Okay? So you want to ask, what happens to my physical system under such a rescaling of space and time? Okay? The Z is called a dynamical critical exponent. Of course, in relativistic theories, so what value of Z will in a relativistic theory Z be? 1, yeah. But for example, in non-relativistic theories, you can have several values of Z. For example, so you can, from the Schrodinger equation, what Z will you get in the Schrodinger equation? So let's write it. So it's I d dt psi. So what is the value of Z for this equation? 2. And in fact, this equation has this conformal symmetry I talked about, the Schrodinger symmetry. But then you can also have other values of Z. So, for example, you can write down theories that are called Lifshitz theories that have something like this, and then you can write something like this. And this guy will have, as you can see, Z equals 3. Okay. So this is a particular exponent that in a non-relativistic system can take different value. Okay. But in relativistic theory, since this has to be it has to be covariant, which means commute with Lorentz transformations, Z has to be 1, yes.
Professor, is it related to anisotropy between space and time? Because in the Lifshitz theory, it's related to the...
Yes, but also here, I mean, space and time in the non-relativistic world are not symmetric in that sense. Yes. Notice that this theory, one difference between this theory and this theory is that this theory has Galilean boost symmetry, but not this one. Okay. So this is an example of a conformal transformation that you're very familiar with, at least intuitively, what it means to zoom in and zoom out. More generally, a conformal transformation is a space-time transformation. The transformation. So, okay, so from now on, I'm just going to talk about relativistic theories, so not to derail too much. So, more generally, a conformal transformation is a space-time transformation that preserves angles. That preserves angles, but not necessarily distances. Okay? So in equations, what this means is that if I take I'm going to be in flat space, I take my flat space metric element. A conformal transformation is a transformation such that I just rescale the element by some uniform constant. Okay? This clearly preserves angles because there's isotropy in this transformation, but it doesn't preserve length because the line element is multiplied by some function of x. Okay? So there are several transformations here that you're very familiar with. So of course you have the Poincaré transformation that have this property for sigma equals 0. They preserve angles but also distances. And a scale transformation, as you can see, rescales the line element by a constant factor, d squared. And tomorrow we will study we will find the most general transformation that has this property. Okay? The most general space-time transformation that you can find that preserves angles. Okay? And in dimensions bigger than 2, this is a finite dimensional set of transformations. Which generate what's called a conformal group. Okay? And obviously include Poincaré by its definition, because Poincaré is definitely part of this transformation. Okay? Good. So this is just to tell you a little bit intuition about what these words conformal mean. You're definitely accustomed to scale transformations. Tomorrow we will study in more detail the extra transformations that come that are part of the conformal group and develop an intuition about them. But for now, this will suffice just to tell you what kind of theories we're talking about. We'll be looking at theories that are not only invariant under Poincaré, but in particular invariant under scale transformations. So these are theories that look the same at all length scales. So one immediate question you may have is that, of course, many of the interesting physical theories have length scales in them. Like, for example, QCD has a length scale, the mass of the lightest blue ball, for example. So you could ask, why do we care about CFTs? They seem like very special things. And there are many answers to this question, so let me just give you a few answers of why they play a central role in our studies of field theory. Yes.
Why does QCD have a length scale?
Dynamically, yes, it has the QCD scale.
What did you just? I think I heard you wrong in that last thing that you said.
So QCD has no scale classically,
Yes.
but quantum mechanically has a dynamical scale,
Yeah.
which is the QCD scale.
And where does that come from?
Okay, so that comes from quantum effect.
Okay. So we'll cover that at some point.
I think you must have covered that in quantum field theory too. Okay, so I'll say it more in words later. Is the statement that the beta function of Yang-Mills is classically zero, but it's non-zero quantum mechanically. Yes, lambda QCD. You have not seen that?
Yeah. We have not seen that it's classically zero.
Ah, okay.
We see that it's
Okay.
mechanically non-zero.
Yes.
That's enough to know the difference.
It is a scale because now the coupling depends on some scale. I will say some more details about this soon. Okay. So the reason the conformal theories are very important is that the asymptotic or the large distance, low energy is the same thing, right? Behavior of any quantum field theory is essentially of two types. One that from some point of view you would say is trivial, where you get a massive theory. So if you go to extremely low energies, there are essentially no local excitations that you can write down. And in the old days, we would say that this theory is trivial. Now, this kind of phase is recently very interesting to condensed matter physics for the following reason, is that even though this theory has no local excitations, it can have non-trivial topological features, okay? And these massive phases of quantum field theory can be described by topological quantum field theories. And there's been a lot of work on this in the condensed matter feature. And even though they have no local excitations, if you put this system if the system has a boundary, so even though the bulk inside the system there is no local excitation, you can get interesting excitations in the boundary. So this is something that if you're taking a condensed matter course, you should hopefully be hearing about. Okay? But the bulk is completely gapped and uninteresting from some point of view, but it has interesting features at the boundary. Okay. And then the other feature that can happen is that if you look at scales much longer than any of the scales of your system, then what you will find is a scale invariant theory, so a theory that's invariant under precisely this transformation. Because if you go to length scale much larger, or energy, or let's say in this language, energy is much lower than any mass scale in your theory, you can integrate out, you can forget about the massive state, which means in field theory jargon, you integrate it out. And at the end, you're going to be left with no massless scales. So the theory will be, by definition, a scale invariant. So in this case, the theory has an enhancement from Poincaré to Poincaré semi-direct with dilatation, which is a non-compact generator, because this lambda I was talking about is takes values over the real line. It's not a compact generator. Okay. Actually, remarkably, this is something that is only very well understood in two space dimensions, to some extent in 4 dimensions, but for example, not in 3 dimensions. Under reasonable conditions, which means that the theory is unitary, locality, and so on, this symmetry is further enhanced to precisely the conformal group, to conformal. So we will see this tomorrow. This means that in the symmetry will have an SO2, algebra if we are in Minkowski space, or SO1, D plus 1 if we are in Euclidean space. Yes?
When you say that the large distance, low energy behavior of any QFT, does it mean that any quantum field theory after renormalization will be conformal invariant?
Yes, in the extreme infrared, yes. That's exactly the point. So at the end of a long RG flow where you integrate to very large distances, you will always find this. Now, you could say that this one is an example of, in the bulk of a trivial theory, is an empty theory. So you always get a conformal field theory. The conformal field theory might be trivial, that there is no excitations, but yes. That's one of the key reasons why these CFTs are important. They govern, so CFTs govern the low energy behavior of quantum field theories. And as such, as we will maybe see in more detail, they provide an ordering in the space of quantum field theories. So it gives a set of relations between the different quantum field theories, and by virtue of knowing which CFTs can arise in the infrared limit of which other one. Okay? Very good. And I'll say more about this later. Very good. So let me give you some examples. So of course, okay, so this is just a general statement. So CFTs are ubiquitous as a description of the low energy behavior of quantum field theory. Now there are certain important equations in physics that are classically conformal invariant. So let me give you a few examples. So you have the Maxwell equation. Also, the Dirac equation is conformal invariant. Okay, can you give me an example of a classically conformal invariant, at least, okay, scale invariant theory in 4 space-time dimensions? So, yeah, okay. I don't want to say more because
5-4 theorem.
the 5-4 theory, yeah. So, is scale invariant. Another example? Young-Mills. So you see that, in fact, most of the usual equations that we study in quantum field theory are classically scale invariant. Okay. Can you give me another interaction that will be scale invariant in 4 dimensions? You choose whatever fields you like.
Can you give an example of not conformal invariant?
Just give a mass. Just give a mass to the scalar field, because then you have a mass scale. Or yeah, or write a 5 to the 6th potential. So what kind of conformal invariant interact? I mean, you're familiar with dimensional analysis in field theory? Yes? So if I give you a scalar field and a fermion psi, what kind of interaction can you make that is scale invariant in 4 dimensions? Sorry? So what is that? How do I write it? Yes. Because this guy has dimension 4. Because this guy has 3 halves plus 3 halves, 3 plus 1 is 4. So this guy is dimensionless. Yeah, it's classically dimensionless. Good. But this is here the thing that's important. This is classically. Okay. Now quantum mechanically. So for example, if you study, I don't know, in lambda phi to the 4, you can have virtual effects of this type that induce scale dependence on your coupling. So this scale dependence is measured by what's called the beta function. So if you have a coupling lambda, this is defined as the derivative of the coupling with respect to scale, is the logarithmic derivative of the scale. Okay? And generically, even though this could be 0 classically, like in all these examples, quantum mechanically this is non-zero. Okay? So quantum mechanically, these theories are not scale invariant or conformal invariant. Okay. And since now lambda, the coupling has a non-trivial dependence on the scale, what we say is that this triggers some renormalization group flow. Okay, so now we're going to say a few words about the physics of these, just qualitative features about the physics of these renormalization group flows. Okay, so the physics of an RG flow depends on which operator triggers it. Okay, so you have an operator O that has dimension delta, and you look at your Lagrangian. Then the coupling associated with that operator will have, what's the dimension of this coupling? Just by dimensional analysis.
Delta minus D.
Sorry?
Delta minus D. Or D,
Try again.
Huh?
Try again. It was close, but
D minus delta.
D minus delta. Yes. Okay. So in order to understand what happens if you start with a theory and you perturb it by such an operator, yes.
When you ask for the dimension, you mean the mass dimension, right?
Yes, the scaling dimension. As more technical, is the scaling dimension, yes. In order to understand what happens to your theory once I deform by this operator, we will study the scale, what happens when, how does this coupling change with scale, okay? So one useful way to think about it is that if this, I can define a dimensionless coupling constant given a dimension-full coupling constant by introducing some mass scale, mu, which will have to have, okay, so tell me that I don't screw this up. So lambda delta minus D, right? So now the beta function of this coupling, classically, is D mu of lambda bar. It's going to be delta minus D times lambda bar, right? So now you see that the behavior, so by integrating this equation, which is trivial, right? You will understand what happens to lambda bar as you go to large distances, so as mu decreases. Okay? So what you find is three possible things. So if delta is bigger than D, it means that the coupling or the operator is irrelevant, which means that it dies towards the infrared. This just follows from the fact that this coefficient is positive. So if you integrate this, you see that the lambda bar decreases towards the infrared, and it's called irrelevant. You must have seen this language, I assume. If the dimension is smaller than delta, it's called relevant. It's exactly the opposite. It grows towards the infrared. And if delta equals D, it's called marginal. So actually, it means that it doesn't run at all, essentially. Okay?
Why do you look at infrared?
Sorry?
Why do we look at infrared?
Because that's what we usually do. We have some, in field theory, we have some microscopic rules that we know at some length scale, and you want to know what phenomena can happen at low energies. Now, the fact that this operator is marginal, typically for this to be preserved to all orders in perturbation theory, this requires some extra symmetry beyond what we were discussing, okay? So it requires some kind of a special feature that the theory has an exactly marginal coupling, okay? So what we see is that the operators that are important at large distances are the relevant operators, because the irrelevant essentially die off. And at large distances, they have very little effect on the physics. That's what it means that they're irrelevant, essentially. So this gives a rationale for the notion of universality in physics. this leads to the notion of universality. I mean, which between friends says that if you have a system with certain symmetries, that the long distance behavior of that system, which may be very different, you could be discussing magnets, or you could be discussing water, or so on, will be governed by a finite set of relevant operators. The relevant operators are the ones that dominate at very large distances. So if you have a physical system with certain symmetries, they will have to be described with the theory with those symmetries, and potentially with a finite set of relevant operators. One thing that's very important is that and you can check in your mind with the examples that you know, is that the number of relevant operators in any given theory is always finite. Is that clear? Okay, so for example, in Fordham, okay, is it clear or not? No? Okay, so take a scalar field in D equals 4. Tell me all relevant operators that you can write down.
The mu phi squared, phi squared, phi to the 4.
Okay, can you say it louder?
Okay, the kinetics terms. I mean, the mu phi.
Well, that's actually marginal, but
Okay.
Everything to power 4.
yeah. So essentially phi squared, phi cubed, and phi to the 4th.
Is that a property of renormalizable theories?
Well, that's in a way that gives a rationale why renormalizable theories appear in the low energy description of physical systems, because the low energy description are precisely so at low energies, the couplings that are important are the relevant, or sometimes it's called renormalizable. Even though I don't like that language very much, but in the old days, there was a bit of a confusion about the logic of the story. Here, the way I want to present the logic is that at very low energies, the only thing that matters are the relevant operators. And that's why at very low energies, you typically are described as a renormalizable theory. So you see that, so this explains universality, because even though you started with something very complicated at short distances, at the end of the day, the theory will have to be described by a theory with such coupling. And well, I assume that you have heard this word of universality before in the context of statistical mechanics, but this kind of a field theory-ish way of understanding where it comes from. Okay. Good. And now, maybe as an exercise, you could try to write down all relevant couplings. By the way, lambda phi to the 4 quantum mechanically becomes irrelevant. It's an example of this type that is classically marginal, but quantum mechanically the beta function is positive. So actually, it's what's called marginally irrelevant operator. So now what we can do is we can start with some CFT unperturbed by a relevant operator, or several, and ask what happens in the infrared. If we perturb by an irrelevant operator, nothing very interesting will happen, because the irrelevant operator dies off as you go to the infrared. And what can happen is that you go from one CFT at short distances. So you start with some CFT, 1, you perturb it, and at the end of this long energy flow, you get another CFT2. Okay. Now, how would you know that you have obtained at least a scale invariant theory by perturbing by an operator? That will happen if there is if there is a 0 for all the couplings in your theory. If you have a 0 for all your beta functions in the theory, it means that the theory is scale invariant. Okay? So this would correspond to this CFT in the infrared. Okay? And the thing that's remarkable is that even though you started with some theory that described by some particular description, the physics or even the degrees of freedom that you can get in the infrared looks completely rearranged and different with respect to the one that you started with in the ultraviolet.
So again, we start from a CFT, we perturb it with some relevant operator, and then we go to infrared.
Yes.
And we get another CFT. That's the idea.
Yes. If you can tune your initial conditions such that you have a zero of all your coupling.
Okay.
Because generically what can happen, and I'll show some flow diagrams, you can get a massive theory.
All right.
But you can tune, if you can tune to find a zero, then you're going to have a CFT. Typically, to flow to a CFT, you have to do some kind of tuning. This you see, so one place in which you have seen, hopefully, scale invariant theories in the context of statistical mechanics. So there, if you go to a critical point, the experimentalist is doing the tuning, right? You have to go to the right temperature. So that, in the language of field theory, means that you have to tune your coupling such that you hit a zero of the beta function. So then you can see that there can be a very rich pattern of flows from one CFT to the next. Okay, so you start with some CFT in an ultraviolet, and you get another CFT in the infrared. Okay, and as I mentioned before, now let me say it a bit more precisely here. That CFTs induce an ordering in the space of quantum field theories. The reason is the following. It is known, can be proven, it's an important result in quantum field theory, that if you have some CFT1 and you perturb by a relevant operator and it gives you a CFT2 in the infrared, imagine this exists, you know that this is true. It implies that there is no flow that you can ever write down that will allow you to go from CFT2 to CFT1. This doesn't exist. Okay? So in some sense, RG flow is irreversible. You can go only in one direction. If you can go from here to here, you can never go from here to here. Okay? So this you can think of in the space of field theories providing a certain height. You can think of coming down from some height function, and you can only go down in one direction, essentially. More formally, what we can do, and I hope to discuss this in one of the lectures, we can assign a particular observable to a CFT, which we will call generically C. We'll call C generically. That if you have a flow like this, has a monotonicity properties. Tells you that this quantity evaluated in the ultraviolet is always bigger than quantity in the infrared. Okay? So this provides this ordering I was telling you about. And this ordering that I was just telling you in words is encoded by this inequality. C always has to decrease from the ultraviolet to the infrared. Okay? And this endows the space of conformal field theories with kind of a foliation structure that describes this reversibility of the flow. Okay.
And given any two CFTs in which we can calculate this inequality, we can find a relevant operator that will give me one.
Yes. Of course, yeah. As I said, this quantity C is an intrinsic property of the CFT, and actually, this C has a physical meaning. So I'll just say the buzzword. I may come back to this later if there is time. You may have seen this in one of your courses. This measures the entanglement entropy of a spherical region. In the conformal field theory. Have you seen this buzzword, entanglement entropy, before? And in quantum information or something or other? Is the answer no or yes?
How exactly does it correspond to the ordering of the cube?
No, say that C, you can ask, what is the physical meaning of C?
But
And
how
if-
does it correspond? Because this quantity assigns the ordering
Yes.
of the theory.
Well, it just tells you that entanglement entropy must decrease along RG flows.
Okay.
So this is something that you probably have seen, actually probably in your first quantum mechanics course where you talk about density operators and so on. If you have a density operator, you can define the von Neumann entropy. And this is what this object is. So this is an interpretation that's valid in all dimensions. When the space-time dimension is even, this C is related to what's called conformal anomalies, which I will describe in one of the lectures. So these are important quantities of your CFT that will tell you information about what kind of flows are possible and which ones are not possible. Okay? Good. So now, in that picture somewhere, here, of this RG flow, typically, if you think from your usual quantum field theory perspective, that you start with some Lagrangian and so on, this CFT that you get here is typically not, so the zero that you're going to get here will happen in a regime where perturbation theory is not valid. So this we will call a long RG flow. This CFT is strongly coupled with respect to the couplings of the ultraviolet theory. Okay? So this is not a perturbative RG flow, and then we have to be clever about constructing sets or give arguments why do we think that such a RG flow exists. But you can also be clever and construct examples of perturbative RG flows. What do I mean by that? So these are examples where you start with some CFT in the ultraviolet, and the CFT in the infrared has a zero such that lambda star is still much more than 1. So it means that you have control, perturbative control of the physics of the second, of the infrared fixed point, okay? So there are, what did you do with the eraser? There are two basic examples. I mean, there are many examples, but let me give you one that's is very important and famous, and in fact, in some sense, the Nobel Prize was given for this in the context of critical phenomena, as I hope to explain a little bit. Okay, I'll be brief. So I want to construct perturbative RG flows. So the first example was what's called the Wilson-Fisher fixed point, or fixed point, or CFT. There are different ways you can say it. Another one, but given that time, maybe I will not describe. So this happens in scalar field theory in 4 dimensions, but you will see that we'll do something kooky about the dimension. Another famous example that happens in gauge theory. So this is in scalar theory. And then there's something called the Banks-Zaks fixed point, CFT, that happens in Yang-Mills theories. Yang-Mills plus quarks. Okay? But once I explain the physical mechanism here, you will understand what the hack is. So this is a bit of a hacking that you have to do to be able to construct a CFT that's perturbatively reliable. Okay? So let me tell you what the hack that this Wilson and Fisher did. So we start with lambda phi to the 4 theory. Okay? And we know from Feynman diagrams that the one-loop beta function is positive. Okay? And in fact, it goes like, can someone tell me, just so there is some more interaction, with what power of the coupling does the beta function of phi to the 4 go?
Lambda squared.
Lambda squared, yeah. So now the idea is to do something so that to construct a zero of the beta function. Now, how could you do it? So if you're in 4 dimensions, the lambda, we already said, is dimensionless, right? But what could you do? So I'm going to give you a hint. So in what direction should I change the dimension to make lambda? So what I want to do now is, here's the idea. So I have beta lambda has a one-loop correction, which is let me say it like this, that's positive. And now, so this is one loop. I want to give it a 3-level contribution such that I can find a zero. So that means that this has to be negative, okay? Which means that it has to be a relevant operator. Because remember that I said that the beta function goes like d minus delta, okay? So one way of doing it is by, which sounds crazy, but is to change the dimension of space-time from 4 to 4 minus epsilon. So if I make the dimension from 4 to 4 minus epsilon, then lambda is relevant. Do you see that? This is just a simple arithmetic that you can check that lambda will have a mass dimension proportional to epsilon. So that means that this guy will have a minus epsilon here. Because, minus epsilon lambda. Okay? That just measures the dimension of lambda, which is epsilon. So now what you can do is construct a fixed point by essentially imposing that this is 0, and you find that lambda star. So you want to find a 0. So you get something that where lambda star is of the order of epsilon divided by a. Okay. So what you have done by doing this hack is you have found a non-trivial fixed point that's close by. So here, this is how you can think of it in pictures. You start with your original lambda phi to the 4th theory, and here there's a fixed point. So you have two parameters in this plot. You have two couplings. You have the mass and the lambda phi to the 4 coupling. And what I've done is to trigger an energy flow from the free theory, where lambda equals 0, to this lambda star theory. But, OK. And if you draw, I mean, these are differential equations as a function of the scale. So these are, by the way, the arrow always means, it means the direction towards infrared, okay? How it changes towards infrared. So this is an example of an RSG flow diagram. So here you have your free field theory. Free field theory is an example of a conformal field theory. And this point here is the Wilson-Fisher CFT. And here it is the value of the coupling that's still very small. Okay? So I can use Feynman diagrams, perturbation theory around the Gaussian or free field theory fixed point to compute all the information I want about my Wilson-Fisher, about my CFT. Okay? So this is a kind of a simple example of a technique that has been used very powerful. And as I said, Nobel Prizes were given to this to learn about the physical properties of a CFT, of a non-trivial CFT. This is a non-trivial CFT in the sense that it's interacting as opposed to this one, which is just free. Okay. Now, the one place in which this has been used is in the discussion of the three-dimensional Ising model. Okay? Let me tell you very briefly what the connection is. So there's some lattice Hamiltonian in 3 dimensions where you have spins on the sides. Okay? That has kind of the following phase diagram, roughly speaking. So this is magnetic field, this is temperature. There is a critical temperature where the theory exhibits a scale invariant. So that's the critical point, which is governed by some CFT. Okay. And then here, okay, so this theory has a Z2 symmetry. I can reverse the spins, and it has a Z2 symmetry. By the way, just like this theory has a Z2 symmetry, I can send phi to minus phi. Now, at very low temperatures, you get, depending on the value of the magnetic field, you get, you have a first-order phase transition across this line. And since the magnetization takes a particular value, Z2 is spontaneously broken. While here, a Z2 is preserved, okay? Now, the way to think about it, I mean, that was the idea of Wilson, is that if you study this theory near the critical point, you can describe the fluctuations of the spins by a continuum quantum field theory, which is precisely this one. It has the same symmetries, and it's governed by these two relevant coupling. Okay? This coupling, and tuning to the critical temperature is essentially tuning to the massless theory. Okay? Good. So what Wilson and Fisher did is essentially try to access the physics of this fixed point using this Lagrangian by starting with the theory in 4 minus epsilon dimensions, do perturbation theory. Here, there is then you do some kind of Padera summation of the perturbation theory, and then extrapolate. Of course, the Ising model lives in 3 dimensions. So at some point, you have to do something that is not really justified. But you take your Padera summation, and you evaluate it at epsilon equals 1, which is d equals 3. Okay? And in this way, this was used to predict the critical exponents using this uncontrolled approximation for the critical exponents of the 3D Ising model, which is in the same universality class as the critical point of the vapor, the water-vapor transition in water, say. Okay. So this is a very concrete example of how these conformal field theories were used and this technique to study the behavior near the fixed point. You should now think by yourselves, what would you have to do to your Lagrangian field theory to describe this phase and this phase? Can someone tell me? How would I describe the phase with the spontaneously broken Z2 symmetry? So by tuning the mass to 0, I describe the critical point. How do you describe this one? Notice that in some sense, if I make m squared negative, very negative, phi will have an expectation value, and this will break spontaneously the Z2 symmetry. So in some sense, this would correspond to mass squared very, very negative. This would describe the spontaneously broken phase, while you can describe the unbroken phase by taking the mass to be very large and positive. Because so here you have the expression phi is non-zero, and here you have the expression phi equals 0. So you can see by this continuum field theory can rather directly map out the phase diagram that you know from lattice Ising model. Okay. So and this is just one example of how, apart from this grandiose picture of CFTs being important in the study of the space of quantum field theories, CFTs are also directly relevant for nature, and this is a very particular example. They describe, let me give you 2 examples. So they describe the critical behavior in statistical mechanics near a second or higher order phase transition. So CFTs are also relevant, directly relevant for nature. So there are 2 basic things. So one is critical phenomena in statistical mechanics. So here the idea is, again, you study some lattice system or something, you tune some parameters, which is, in the field theory language, means that you go to the zeros of the beta function, and you go to critical points where the system has no intrinsic length scale, which means the correlation length goes to infinity. So, okay, so maybe I should say something about this. So if you study the correlation function of, in this case, would be spins, but this could be density of water, whatever, the connected two-point function, generically, at an arbitrary value of the parameter, this will have exponential decay. And this defines a length scale, which is the correlation length. At these critical points, what happens is the correlation length goes to infinity. Okay? And then you have no length scale, and the system is described by a scale invariant field theory. Okay? And then the whole game in critical phenomena is to study the behavior of thermodynamic quantities as you approach the critical point. So typically, the critical point, you have to tune, say, the temperature. You can have also critical points that you have to tune more than one parameter, like temperature and pressure. They're called multi-critical points. And essentially, what you want to do in critical phenomena is study the divergence or the behavior of thermodynamic quantities as you approach the critical temperature. So, and this defines critical exponents. So let me just quickly tell you the divergence of the correlation length as you approach the critical point, the behavior of the magnetization, as you approach by changing the temperature of the magnetic field, the heat capacity diverges, also the susceptibility diverges. So this defines a whole bunch of numbers, okay? And finally, at the critical point, this guy has power law behavior. Okay? So the name of the game is what people in statistical mechanics and people that do this in the lab are interested in computing these numbers, okay? And the thing that's amazing is that if you scale symmetry alone, gives you a whole bunch of relations between these parameters that you wouldn't have otherwise expected. It just follows from a scale invariance. This always happens when you have a new symmetry. You get relations between things that you didn't know before. And it turns out that you can use this scaling symmetry to relate all the parameters are determined in terms of two parameters, of two critical exponents. So, and this is observed experimentally, by the way, which will be nu and eta. And actually, this is directly related, as we will see, to the scaling dimensions of operators. So when you have a conformal field theory, the operators have a certain scaling behavior under scale transformations. And these critical exponents are the dimensions, measure the dimensions of the operators under a scale transformation. So they have a direct interpretation in the continuum field theory. Okay, just quickly, the other place where these CFTs are directly relevant in nature is in quantum phase transitions. So here, in statistical mechanics or critical phenomena, the phase transitions are driven by thermal fluctuations. Here they're driven, so this happens first of all at zero temperature, and they're driven by quantum fluctuations. So here, what happens is that you have a Hamiltonian, you have a ground state, and for generic values of the parameters, there is a gap to the first excited state. Okay? And then what can happen is that if you tune the parameters of your Hamiltonian to some critical value, this gap goes to zero. Okay? So then all of a sudden you have a scale invariant spectrum. And then again, this is governed by some CFT. Okay? A simple example of this is you take the Ising model, quantum Ising model in one dimension. So you have the sigma z polymetrics, and then you turn on a transverse magnetic field. The spectrum of this Hamiltonian takes this form, has a gap, but if you tune J to 1, you have it's described by a CFT. And actually, you will probably study this CFT next week. This is described by a CFT in 1+1 dimension of a free fermion. So you're going to study all the properties of this critical point by this continuum field theory. Okay. So I was just saying words. Other places where CFTs are relevant, not directly to nature yet, but at least in interesting areas of theoretical physics, Well, okay, so one thing I should say is that one thing that's amazing about CFTs is that you can solve them by imposing consistency conditions. So just essentially by pure thought, especially in 2 dimensions, using pure thought, you can just solve explicitly for all the critical exponents. Okay? This is very different than the way we deal with quantum field theories, where we are tied to Feynman diagrams. This CFT, in some sense, the Ising CFT, sometimes called Ising CFT. In a very definite sense, it's strongly coupled. There is no sense in which you have a small parameter anywhere. But nevertheless, one can, using consistency conditions of conformal fluid theories that we will describe, you can solve, at least you think you solve. In 2 dimensions, you can definitely solve. In 3 dimensions, you will see that there are some assumptions, but you can essentially solve the theory just by imposing consistency condition, which kind of is a theorist's dream, because consistency tells you what the answer is, essentially. The other thing to say is that these, of course, are relevant for the ADS-CFT correspondence, if you care about that. You have a CFT with certain properties. It may be dual to some quantum theory of gravity that lives in asymptotically anti-de Sitter space. It's also relevant for perturbative string theory. Let me just say it briefly here. CFTs in 2 dimensions are directly related to string theory. And here, this equation that we wrote many times, that the fact that the beta function vanishes tells you that the theory has a graviton, a gluon, quarks, and they lead to Einstein's equations, Yang-Mills, Dirac, and so on. So here, it's remarkable how these fundamental equations in theoretical physics are a direct consequence of conformal invariance. So conformal invariance is extremely powerful in string theory because it dictates all the dynamics of the theory. And finally, there are many connections between CFTs and mathematics that I will not describe in this course. So tomorrow, what I'll do is I'll start systematically showing you how to essentially use symmetry to determine as much as one can what the form of the theory is, without any assumptions about Lagrangians or anything like that. Okay? So we'll continue tomorrow.